In this video, we're going to learn about something called related rates. Rate meaning speed at which something is changing. So we're going to express those as derivatives because they're going to be changing all the time. And then somehow they're going to be related through an equation. So again, these are going to be problems involving two or more related quantities. They're changing with respect to time. They're changing over time, but time is not going to be a variable in the problem. So we do need to use implicit differentiation. If we're talking about rates of change, we are going to interpret those as a velocity. So we're going to write them as derivatives. And our notation is going to be the derivative of whatever we're talking about with respect to time. So let's just dive on in. So example 1, a crowd gathers around a movie star forming a circle. So a picture in a lot of these problems is very helpful. The radius of the circle is increasing at a rate of 2 feet per second. So it's always changing. So I want to identify here a variable because it's not a constant value, it's a changing value. And because it's increasing, it's a rate, so I'm going to express that as a derivative. I'm using this notation. And I'm going to use r for radius, so the derivative of r with respect to time is 2 feet per second. And I chose r here because that's the variable I chose for radius. Okay, now we're going to look at the question. The question says, how fast, so again, that's a speed or a derivative, is the area, so I'm going to use A for area. So this is the speed of the area, and this is my question. How fast is the area increasing at the exact moment when the radius is 5? Now, I'm going to be careful that I don't use this number on my picture because the radius is always changing. It's not 5 all the time. So this is the number I'm going to use after I take my derivative. Now, the hard part about these questions is that you have to come up with a formula to relate these together. This says I need to take the derivative of the area. So I need a formula that has area in it. And since we're dealing with a circle, the most obvious formula to start with is the area for a circle. Now we're going to take the derivative because that's what I need to find. So in this case, in all of these problems, we're respecting t. And t is not a variable in this problem. So we are going to have to use implicit differentiation with every single variable. So the derivative of a with respect to time is dA dt. Pi is a constant, so my 2 is going to drop down. The pi stays there. The radius is some changing value. And now I'm going to multiply by the derivative of r with respect to t. And at this step, hopefully, you have all the information you need to find your unknown. So we're plugging in now everything we know. So dA dt is what we're looking for, so it stays dA dt. We know 2, we know pi. At this one particular moment, our radius is going to be 5. So I'm going to plug in 5 because that's what I'm trying to find. We're trying to figure out what happens when the radius is 5. And then I know the speed of the radius is always 2 feet per second. And so now we're just simplifying. So I know that the area is changing. In this case, 5 times 2 is 10, and 10 times 2 pi is 20 pi. So the area is changing at a rate of 20 pi feet squared per second. I used a unit squared because this is talking about the speed of the area. And that's it. So a more complicated example is going to have a little bit more in it. So a ladder is 20 feet long. We can use this number because the length of this ladder is not changing. This is a constant value. It says the bottom of the ladder is sliding away from the building. So when the bottom of the ladder slides away, that's going to increase the value of x. So that's telling me here how fast x is increasing. So the distance of x is changing at a rate of 2 feet per second. That's the speed at which x is getting bigger. The question is now, how fast is the ladder sliding down the wall? So that's asking me to find the speed of y. So I'm going to write this down, the speed of y. exactly at the one moment when the top of the ladder is 12 feet above the ground. So that's saying exactly at the one moment when y is 12. And y is not always 12, so we're not going to use that number in our picture. So our job now, again, is to find the derivative of y. So I need an equation that has a y in it, and I also know the derivative of x. So we really want an equation that has an x and a y in it. And if we notice from our picture, we can use the Pythagorean theorem. So I'll have x squared plus y squared equals 20 squared. And now I'm going to differentiate. So remember, I'm respecting t, so every variable has to have implicit differentiation. So my derivative here is 2x times its derivative plus 2y times the derivative of y with respect to t, and the derivative of a constant is 0. So again, now it's my job to start plugging things in, and hopefully I can find dy dt. So I'm plugging, I know what 2 is. I don't know the exact value of x, but I do know the exact value of y at that moment. So I can use this triangle to figure out what x would be at that moment. So if y is 12, I know the ladder is 20, I can find the value of x by using the Pythagorean theorem. So we have 12 squared, plus x squared equals 20 squared. So if I solve, I get that x equals positive and negative 16. And since x represents a distance, I'm only concerned with the positive. So I can plug in 16. I can plug in dx dt, which was given in the problem. I know the value of y is 12. And then dy dt is the unknown that I'm solving for. So if I simplify all of this, I'll get 64 plus 24 dy dt equals 0. And continuing then, 24 dy dt equals negative 64. Finally, I can divide by 24. And I see that dy dt is decreasing, meaning the y should be getting smaller. You can reduce if you want. You can divide everything by 8 and get negative 8/3. And here we were measuring in feet per second. So since this is the distance of y, this is just going to be feet per second. So y is decreasing at a rate of 8/3 feet per second. As the ladder is falling down the building. So here's our strategy. You can read through this if you want to, but it is very important that we're going to identify and label everything we know and everything we don't know. A picture really helps. We need to come up with an equation. This is probably the hardest step. Once we find that, we take its derivative and we plug in everything we know. In this example, I will actually go through during class because my video is getting kind of long.